Hi all, welcome back to time series analysis course. Today I'm going to talk about time series statistical models. First, we will talk about white noise. WT, suppose, is the collection of uncorrelated random variables with mean 0 and variance sigma square. We are not talking about what distribution it is. So we're writing it as WT is a IIT random variables with some distribution F with mean 0 variance sigma square. Now if you choose F to be Gaussian, then you will have a WT follow IIT normal 0 sigma square, and if you choose F to be Laplace distribution, then you will have a Laplacian white noise. Here I have simulated Gaussian random variable independently from a normal 0 sigma square distribution, and then I plot them over time as sequentially I simulated, and each iteration over 1000 iteration I simulated, and I plot them over iteration and then join them with a straight line so that it will be a time series plot. And you can see that since it was from mean 0, so all the values are hovering around 0. The horizontal black line represents the 0 and the values are hovering around 0. Here is the histogram of the same white noise data, and this black curve is the density curve of the Gaussian distribution. Here I am presenting Laplacian white noise. In the Laplacian white noise, you can see again it is hovering around 0, just like Gaussian distribution. The only difference is it has this, you can see that the scale was between, for Gaussian white noise it was between minus 0.3 and 0.3. Here it is between minus 0.6 and 0.6. So Laplace distribution tend to observe a slightly higher heavy tail, like very large or very small observations. Next, we will talk about moving average. Consider replacing WT by an average of its current value and its immediate neighbors in the past and future. So Vt we defined as a 1/3 times Wt minus 1 plus Wt plus Wt plus 1, which leads to the following series. So here is the Wt, the original Wt from the Gaussian distribution, and then if you calculate the white noise, you can see that some jitteriness is being reduced from the Gaussian white noise, but it still follow a similar pattern in terms of the as a series. Next, we will consider another new model called autoregression model. Suppose we consider the white noise series Wt as input and calculate output using the second order equation, xt equal to xt minus 1 minus 0.9 xt minus 2 plus Wt. Now here xt, you're taking two kinds of inputs. One is xt minus 1 and minus 0.9 times xt minus 2. These two and the Wt, where Wt is a Gaussian white noise. If you know here what is the value of x0 and what is the value of x1, then you can simulate the W3 and that will give you the x3. Now you know x2 and x3, you plug x2 and x3, you simulate W4, that will give you x4. In this way, you can simulate the entire series if you know what is the value of x0 and x1. I have simulated a distribution series from this autoregression model, and you can clearly see the series is hovering around 0. However, it is very different from the white noise, Gaussian white noise. Clearly, it has some heavy, very different pattern than Gaussian white noise. Here, if you see that this is the original series X series and this is the lag series, I have taken a snippet of the series. So these values is the lag value of this particular value. This is the time point 2, you are observing that previous value is the lag 1 value. Now you take that and you plot it, print it here, or you place it here. Similarly, this particular value is the lag value of the third value. This is the second value. This is the lag of the third value. So now you take the second value and print it here. So now you can say that in the second column is the lag column. This value is the lag value of the previous value. Now on the x-axis I plot this column and the y-axis I plot this column. So clearly you can see that my xt is a function of xt minus 1. So I can fit a regression, but here my xt is regress on the previous value. So that is why this particular regression type models are known as autoregression. When you are regressing on the predictive model from your own historical values as your feature or as your predictor. Now I'm going to talk about a very popular model called random walk model. A model for analyzing trend is the random walk with drift model can be given by xt plus delta plus xt minus 1 plus wt when t runs from 1 to ... and with some initial condition x0 at 0. Wt is white noise and delta is called drift. When delta is 0, model is called simple random walk. In the random, you take the random walk model xt equal to delta xt minus 1 plus wt. Now xt minus 1 you can write it as delta plus xt minus 2 plus wt minus 1 within bracket. Now you release the bracket or remove the bracket. What you got is delta plus delta 2 delta here. You got xt minus 2 and wt minus 2. So xt minus 2 come here and wt minus 2 and wt can be plugged in here, bracketed here. Now you got xt minus 2. You can write it again. You kind of use this recursion to write xt minus 2 as delta plus xt minus 3 plus wt minus 2. So then if you remove the bracket, you will get 3 delta plus xt minus 3 plus wt minus 2 plus wt minus 1 plus w2. If you keep doing it in this way, what you will get is after t steps, you will get t delta plus x naught plus summation j equal to 1 to t wj. Now x0 is 0 as our initial condition. So the model reduces to t delta plus summation wj, j runs from 1 to t. Now what I can do, I can simulate this wj, create a cumulative sum for at t, and then if I plot them. Now if delta is 0, then you can see the series will behave like this. But if delta is 0.01, then it's create a angular effect, and this effect is typically called the delta effect of the random walk. Many realistic models for generating time series assume an underlying signal with some consistent periodic variation, contaminated by adding some random noise. It is easy to detect the regular cycle air passenger data. In the air passenger data, we have a straight trend, almost like a straight line trend, and then we have a periodic seasonality. So we can model this kind of data as trend plus a sinusoidal waveform. Now the trend you can model as beta naught plus beta 1 t, and sinusoidal waveform can be modeled as a times cos 2 pi omega t plus phi, and wt is the white noise. If you simulate wt from normal 0 sigma, you will see somewhat, and you consider the signal part as been known, then simulated series will look like the red curve, which is sort of tight. Then we increase the sigma, then what we are getting, that this simulated series, red series, is much more jittery. Now we increase the sigma to 48, and what we are seeing, that the simulated random signal is much more jittery. So the jitteriness of the time series depends very much on the sigma scale parameter of the white noise. Later we will study the use of spectral analysis as a possible technique to detect the regular or the periodic signal. In general, we should emphasize the importance of simple additive models such as given above in the form xt is some signal plus wt. If I go back, you can see that xt, this entire part is my signal. I am modeling the signal part. This is the mathematical model I am using to model the signal, and this is the random or stochastic part or white noise part. st in this model, this is how typical generic abstract form you can think of. So the st is the unknown signal time series, which we typically try to model using mathematical models with a trained and periodic Fourier periodic term, and wt is a noise time series, may be purely white or sometimes correlated over time. The problems of detecting signal and then in estimating or extracting the waveform of st are of our interest. Next, we introduce various theoretical measures used for describing how time series behave. The correlation is an essential feature of the time series analysis. The most useful descriptive measure are those expressed in the terms of covariance and correlation function. Thank you very much. We will see you in the next video.